Let's now introduce a new topic. From what we have seen so far, we can study circuit with an analytical approach by using series and parallel connection of resistors, current divider, voltage divider rules, Thevenin's and Norton's equivalent, superposition, Millman's theorem, star-to-delta transformation in case we can't do anything else with respect to the previous approaches. Now I want to introduce a method that is called nodal analysis or nodal equations that is based on the writing of Kirchhoff current laws at the nodes and allows us to develop a general method that is well suited for personal computers to solve any kind of circuits. For now, let's restrict our study to circuits where we have resistors and current generators, and we will generalize later to voltage generators and dependent sources. Let's consider, for example, the circuit that is here represented. So the method is based on Kirchhoff current law applied to nodes. So the first thing that we have to do is to label nodes. And to do so, we assign numbers to nodes, assuming one of these nodes as a reference node. We call this node the zero node. So, for example, we can assign the value 0 to the node here at the bottom, and let's call the other nodes 1, 2, and 3. Once we have defined nodes, the second step is that we can assign to each node a specific value of potential that is unknown at the moment. Let's call these potentials phi, and the reference node has a value of potential phi 0 that is arbitrary, and let's put this value to 0. As you may know from the course of physics, potentials are defined up to an additive constant, and we can put this constant to 0 to simplify our calculation. So, if we want to assign the potential, we call the potential of node 1 phi 1, potential of node 2 phi 2, and potential of node 3 phi 3. The potential of the node 0 is phi 0 and is equal to 0. The third step is to write Kirchhoff current law at nodes without considering node 0. And let's consider as a convention the plus sign for currents that are flowing outside the node. In order to write Kirchhoff current laws, let's consider the components that we have in the circuit. The first one is a resistor. The generic resistor between node J and K is called RJK. And let's call the potentials phi J and phi K, and the current that is flowing inside this resistor is IJK. It's clear that the voltage drop across this resistor, VJK, is the potential difference between phi J and phi K. And so, applying Ohm's law, we can easily write that IJK equals VJK over RJK. Or, in terms of potentials, is phi J minus phi K divided by Rjk. So we can write each current as the difference between two potentials divided by the value of the resistance. If we want to simplify the notation, instead of using the resistance, we can use the conductance. So we can write this current as the conductance Gjk that multiplies phi j minus phi k. For the current generator, things are even simpler, because for a current generator, the value of the current is known, and it is the value impressed by the current generator. So, if this generator is connected to nodes J and K, and its value is AJK, we can say that the current IJK is simply AJK. So, we can try to write Kirchhoff current laws at nodes by referring to the value of the current impressed by the current generators, or in terms of conductance that multiplies the difference between two scalar potentials. Let's now consider, for example, node 1. And let's write the Kirchhoff current law, as we said, considering positive currents when they are flowing outside the node. So, in our case, they are positive if they are flowing with these directions. Since the current A1 is flowing inside, we have minus A1. Then we have a current that is the current that is flowing through the resistor R2. We can write this current as plus G2 phi 1 minus phi 2. That is the potential difference across the terminals of the resistor, so that we are expressing this voltage divided by the value of the resistance, or, to simplify the notation, multiplied by the conductance. We can do a similar consideration for the resistor R1, and so we have plus G1 that multiplies phi 1 minus phi 3. And to conclude Kirchhoff current law, this sum equals 0. We can apply the similar approach to node 2. In node 2, we have the current of the current generator that is flowing outside, so plus A2. Then we have the currents that are flowing through R2 and R3. If we want to consider the currents that are flowing out, we can write the current that is flowing outside the node 2 and is flowing inside R2 as G2. This time we have phi 2 minus phi 1. So we have always to put the potential of the leaving node minus the potential of the node where the current is flowing to. And finally, plus G3 phi 2 minus phi 3. And again, this equals 0. Finally, we have the equations at the node 3. Here we don't have any current generator, so we can write this equation as G1 for resistor 1 that multiplies the node 3, the potential of the node 3, phi 3, minus the potential of the other node of resistor 1, phi 1, plus G3, phi 3, minus phi 2, because these are the potentials across the resistance R3, and finally plus G4, phi 3 minus phi 0, and this equals 0. As you can see, we have written here three equations where we have the potentials as unknowns. So the unknowns are phi 1, phi 2, and phi 3. Actually, here in these equations, we also have the value of phi 0, here, but the phi 0 has a fixed value. We said that the reference value of node 0 is 0. So we have exactly 3 Kirchhoff current laws applied to 3 nodes with 3 unknowns. And since we have applied these equations to 3 different nodes, these equations are linearly independent. Now let's rewrite these equations in matrix form. What we want to get is a matrix that multiplies the unknown vectors having phi 1, phi 2, and phi 3 as unknowns. And at the right-hand side, we will have the known terms. That is, the terms that contain the sources of the problem, in our case, the values of the generators. If we take the first equation, the value of phi 1 is multiplied by G1 and G2. So we have G1 plus G2 in position 1, 1. In position 1, 2, for the first equation, the term that multiplies phi 2 is minus G2. And finally, the term that multiplies phi 3 is minus G1. We have in the first equation the value of the current generator A1 that goes to the right-hand side, and so we have A1. If we take the second equation, the terms that multiply phi 1 is simply G2 with a minus sign. Phi 2 is multiplied by G2 and G3, so we have G2 plus G3 in position 2, 2. And finally, in position 2, 3, we have minus G3. At the right-hand side, we have minus A2. Finally, if we consider the last equation, we have minus G1 in first position, minus G3 in the second position, and G1 plus G3 plus G4 plus G4 as the last term. In the last equation, we don't have any generator that is pushing some current inside node 3, and so we have 0. Let's try now to investigate how this matrix is structured. The first thing that we can note is that the diagonal terms, let's say in general G, J, J, contains the sum of the conductances connected to the node J. So if we go back to our example, for example, we can see that at node 1 we have G1 and G2 that are connected directly to node 1. For node 2 we have G2 plus G3, and for node 3 we have G1, G3 and G4. The second property of the matrix is that the generic term G, J, K contains minus the sum of the conductances that directly connect nodes J and K. In fact, for example, if we look at the term in position 1, 2, we can see that it contains only the term that directly connects the nodes 1 and 2. So we have minus G2. For node 2 to node 3, we have R3 here. And so we have minus G3 in position 2, 3, and so on. The last comment is that at the right-hand side, the term AJ contains the algebraic sum of all currents impressed by current generators that are connected to the node J. With the convention that we use the plus sign if the current is entering the node, or minus if the current is leaving the node. Starting from these considerations, we can highlight some properties. The first property is that the matrix is symmetric. In fact, because of the fact that we have in the position JK the sum of the conductances that connect nodes J and K, we also have the same term in position Kj. And so, for example, if we compare the value that we have in position 2, 3, we get exactly the same value that we have in position 3, 2. The second property is that the sum of the rows of the coefficient matrix represent the conductances that are connected to node 0. For example, if we calculate the sum of the rows for the coefficient matrix, we have 0 in first position, we have 0 in the second position, and we have G4 in the third position. And if we compare this result to the circuit, we can check that we don't have any conductance that connects node 1 with the reference node, we don't have any conductance that is directly connected between node 2 and the node 0. And finally, we have a single conductance G4 that connects the node 3 with node 0. And in the circuit we have this conductance here. The sum of the right-hand side terms gives the impressed current, the total impressed current that leaves node 0. If we go here again into the matrix representation of the solution of the system, we have A1 minus A2. And this is actually the total current that is leaving the reference node. In fact, we have the sum of the current of the first generator minus the current of the second generator. Now, let's try to include in our nodal equations also the voltage generators. We have two cases here. The first one is when the voltage generator is connected in series with a resistor. In this specific case, we have between two nodes the Thevenin's representation of a two-terminal component. So, for example, we have E of t and R connected to the nodes J and K. If we have this situation, what we can do is to transform this representation into the corresponding Norton's representation that is made by a current generator that is connected in parallel with a resistor. The value of the resistor is identical to the value of the resistance of the original circuit made of the voltage generator and the resistor, so this value is R, while the value of the current impressed by this generator is the short circuit current of the circuit on the left, that is E of t divided by R. So once we apply this substitution, we have a current generator in parallel with a resistor, and we can use the same approach that we used before, because we have transformed the voltage generator in series with a resistor into a current generator in parallel with a resistor. The second case is when we have only the voltage generator. So we have the voltage E of t that is directly connected to the node J and node K. The consideration that we can do in this case is the following. This generator is also supplying a specific current to the circuit. Let's call this current Ix, because this current is unknown. Now, what we can do is to transform this voltage generator into a current generator, a fictitious current generator, where the current is exactly Ix. And the voltage applied between the two nodes J and K is exactly the electromotive force of the voltage generator. So we can write that for this second component, this current generator, we have Ix that is unknown, while the voltage phi j minus phi k equals E of t. Of course, if we substitute the voltage generator with the current generator, but with exactly the same value of voltage and current of the previous element, we are not changing the behavior of the circuit, because we are still saying that we have a voltage here applied that equals the electromotive force of the voltage generator, and here the current is exactly the current that the voltage generator is supplying to the circuit. Now let's try to see how this works in a real circuit. Let's suppose that we have this circuit where three nodes are used to describe the circuit, and we have 6 elements. One of them is a voltage generator. Now, what we are doing is to transform the voltage generator into a current generator virtually with an unknown current. This is the circuit that we have after the transformation. Note that with this substitution, we are not saying that the current generator has the same behavior of a voltage generator in general. We are saying that if we connect a current generator that is supplying exactly the same current of the original voltage generator, and at its terminals we have a voltage that is exactly the electromotive force of the voltage generator, the behavior for the rest of the circuit is exactly the same. If we consider this second circuit, we can try to calculate the solving matrix by inspection of the circuit, by using the consideration that we have done before. So we will have a coefficient matrix that, multiplied by the vector of unknowns made by phi 1, phi 2, and phi 3, gives the right-hand side that is made by the contributions of generators. In position 1, 1, we have the sum of the conductances that are directly connected to node 1. In this case, we have the resistor R1 and the resistor R4 that are connected to node 1, and so their contribution in the matrix are G1 plus G4. In position 2, 2 along the diagonal, we have to put the sum of the conductances that are directly connected to node 2. In this case, we have G1 and G3. So G1 plus G3. And finally, if we consider node 3, we only have G2 that is directly connected to node 3, and so we can put G2. Now, let's try to calculate the out-of-diagonal terms. In position 1, 2, we should put the minus the conductance that connects directly nodes 1 and 2. In this case, we have only the resistance R1, and so we can put minus G1. Position 1, 3, we have to put the conductance that connects directly node 1 and node 3, but we don't have any conductance that directly connects 1 to 3, and so we have 0. Now let's try to fill this empty space here in position 2, 3. we should put the value of the conductance that connects directly node 2 to node 3. Also in this case, we don't have any conductance, and so we have 0. The nice thing is that we don't have to do anything else to fill this part of the matrix, because we know that the matrix is symmetric. And so we can directly put minus G1, 0, and 0. At the right-hand side, we have to put the value of the impressed current that is directly connected to the node, with the plus sign if the current is entering the node. So in our case, we have for node 1, we have the current Ix that is entering, and so we have plus Ix. For node 2, we have the current A that is leaving, and so we have minus A. And finally, for node 3, we have the currents Ix and A that are connected to the node, and so we have A minus Ix. So this ends the first step, where we have written the equations that describe the circuit on the right. But this is not the end of this exercise, because now we have to recall that Ix is unknown, and we have to add the original equation of the voltage generator. So, the two steps that we still need to do is to move Ix to the vector of unknowns, and the second step is to add the equation of the voltage generator. That, in our case, let's have a look here at the original circuit, is phi 3 minus phi 1 equals E. So, in the end, we add one unknown, but we also add one equation, and so the system is still solvable. If I move the current Ix on the left-hand side as an unknown, we have to change the sign for this contribution in the first equation, and so we have here minus 1, and this minus 1 multiplies Ix in order to give exactly the same value of the equation expressed in the previous system. Here at the right-hand side we have 0. In the second equation, we don't have any term that includes Ix, and so the coefficient that multiplies Ix is 0. In the third equation, we had in the previous system Ix. If we move this to the left-hand side, we have to change the sign, and so its coefficient is plus 1. So in this way, by adding one column at the end of the original system and adding one unknown in the vector of unknowns, we have actually described exactly the same system as before, but with Ix as unknown. We still have to add the contribution of the voltage generator. The equation is this one. We have the coefficient minus 1 that multiplies the scalar potential phi 1, and the coefficient plus 1 that multiplies phi 3. So we have -1, 0, +1, 0, and this value equals E of t. So, if we want to solve a circuit with a voltage generator and a current generator using the nodal equation, what we have to do is first transform the voltage generator virtually into a current generator, but with an unknown current. Write down the equations by inspection, then add another step where the unknown current Ix supplied by the voltage generator is moved to the left-hand side as unknown, so we add also a column in the coefficient matrix and one element at the unknown vector. This additional unknown is compensated by the addition of another equation that is the equation of the voltage generator. So in the end, we have another system. We will see during the practice how we can also include in this writing of the nodal equations also the dependent sources. In this specific case, I added this new topic regarding the nodal analysis in order to give you an idea of what is behind the solvers that are used for the simulation using PCs. So when a computer is solving a circuit, is actually using this specific equation, the nodal analysis equation, in order to solve the circuit. For us, the target of this specific exercise is to write down the equation. I'm not asking you to solve also the equation.